I was computing the magnetons, and I noticed when I went to NIST's code data, the numbers were different. Essentially, what had happened is back in 2017, that had brought up a mystery. It's like, what else is off? There was actually was the Wien displacement law and stuff. We're looking at these different things. It's like there's new information available. And I feel sometimes if there's new information, we work really hard. We try to hone in on something. We get something so beautiful, so elegant. And then all of a sudden experimentation will throw us a curveball and we're like, was not expecting that. And this is what I love about this model is because hyperbolically, of course, it's also based upon a geometric structure of the complement of a knot, and a good knot should tighten up. And I think that's the strength in the model. At least I'm going to claim that. Because as we get that new data, we started to utilize the universal binomial factorization equation. Basically, you have whatever your primary action is. So you got your primary action, okay? And then that's going to be measured by your boundaries. So basically, you can take minimally 5-dimensional ingredients of our universe as we know it to basically build the world as we know it. Time, space, charge, mass, and temperature. And from those ingredients, and go and wolf our mouth and totally try this yourself. Sometimes you'll see angles, sometimes you'll see current, but current has a direct relation between charge and time. And just seeing how these different building blocks come together, we can essentially write a prescription for how to reverse engineer reality. So we have that, and then we have our terminal action. So by basically taking this, I might be getting this wrong. We have this, but the terminal action is actually composed of, I should have just done a box like this. The terminal action is 1, and we settled on plus, this is the geometric action. So we have action of the terminal, and then we multiply that by, it's the terminal inversion boundaries, which is Planck length times the Planck mass over the Planck charge squared. But basically this comes out to be exactly 10 to the negative 7. And this was something that took you a while to notice, because as we're going through and we're calculating using these different equations for the constants of nature, when you go back and forth and we're using these different conversion factors, after a while, once you start getting out to around 7 decimal places or so, they don't quite add up. There seems to be a little bit of a difference there. And that little bit of a difference there is one of the reasons why apparently NIST, they're redefining SI. They're attempting to create as coherent a set of units as they can. So what we found for a couple of these constants, they cut it off at 10 decimal places, because we used to have a couple more decimal places, but we'd have so much error. So they're bringing it in to, this is what we have a high confidence level to the best of our knowledge at the time, given the equipment that we have. So as these tighten up, we're going to be able to hone in more and more, I claim. And yeah, we went through these calculations and everything, and it seems to be getting simpler. The geometric actions, you start to see a lot of things that are working into it, whether it's the golden ratio, the Fibonacci series and everything. And it's so beautiful. I feel like a lot of human beings, we've had intuitions to these different things. I find this stuff fascinating.
This week has been pretty phenomenal, as he has just been talking about. He alerted to me to the fact that some of these constants have been updated since the list I've been using, which nothing better ever happens for a scientist, right? So to have better data, to have measurements with more significant digits, that's the best thing you can do. Everything else is making sense of the data. So we got to take the exact same method now, and all the numbers who had more significant measures, redo the exact same thing and see what the geometry comes out as, right? Mm-hmm. All right, so we're going to do a few of them. We'll start, of course, with the simplest of all constants, or the most symmetric of all constants, the only one that has primary boundaries that are equal to the terminal boundaries. So magnetic constant has a primary action, has a primary set of boundaries that are equal to its terminal boundaries. So what we want to solve for with the magnetic constant under this universal binomial factorization equation, its dimensions give away that its primary boundaries are the same, that Planck length, Planck mass, Planck charge squared, right? Same thing right here. But we have to solve for the primary action that's being applied to that arrangement. So we have the number, we have the measurement of the constant of nature. You can easily plug that in, and you want your number to be right within somewhere around 7 significant digits. That's what you're searching for. So you find the number here. This one's going to be pretty easy. For anybody a little familiar with geometry, you're going to find a number pop up that's pretty easy to make sense of. Right? What does 4 pi represent?
That's a sphere.
A sphere. Great. Okay. Over here, but now we just need to solve for the terminal boundaries.
Right.
Okay. Before we solve, let's take our partition parameters. We want to form a two-dimensional balance. And under a two-dimensional balance, you can square and square root and still end up the same. That's your two-dimensional balance. Be a one-dimensional balance. Let's recap. If you have a one-dimensional stick, so you have one stick and it's 1 meter long. So you have two properties. You break the stick in half. Now you have two sticks that are 1/2 meter long.
Yep.
The product of the properties are still the same, but you have this balance, this change. If you do one action, it causes another action. And in general, if you split something in half, you've also doubled something else. That's for one-dimensional features. For two-dimensional features, this is the balance we're interested in. So that means we're going to take all of our partition parameters for our hyperbolic vortex equation, G1, G2, G3, G4, and we're going to square root all of them. But we're also going to square all of them, and we're going to use only these pieces to fit against these pieces to make our balance. That would be our most symmetric fitting of the partition parameters themselves. So the big clue that will jump out if you've been following this for a while is you probably recognize that if you add all of these together, you get -4 pi, which is pretty familiar here.
Yeah.
So you can see right away there's a partition way to match what we get on the front from just our partition parameters, and that's half of them. So you might wonder, can we make the terminal action out of the other half? Can we balance this fitting of the same boundaries against themselves as being that simple?
It's a good question. Is it?
Well, when we look, we find that we take the two-dimensional j's divided by the one-dimensional j's, all square roots. So take all square roots, put the two-dimensional ones on top, the one-dimensional ones on bottom, and now they're in a product relationship, not a sum relationship. So there's inherent sum to product combination of the partition parameters themselves under two-dimensional balance. Great. That's what it comes out as. Beautiful.
But that's just multiplication and taking the square root of. These are like some of the basic factors that we were taught in different mathematical classes if we were blessed enough to go to school.
Yeah, I think that's what the big powerful thing we're trying to say right here. If you read algebra, right, if you can train yourself to read algebraic sentences, to get your mind to see what's being said there, it's a very powerful skill, just like learning how to read in any other tongue, right? This is a structured power skill, though. It goes up in its power the more you learn. So reading the algebra here, just interpreting what all the symbols mean, puts together the story. The gravitational constant also is one of the ones that updated. Okay, so we get to go check again and put in the actual updated new number here in our process, right? Which means it's going to have a different output. So a better measurement leads to a better window into what's going on, right? All right. Gravitational constant. It has dimensions of what? Length?
It's length cubed over time squared and then mass.
And then we have to solve for its primary action. Of course, if you check, you just put those numbers in already. It's
pretty close.
already get this, right, for the first few digits. So
Yeah.
its primary action is 1, so I'm not going to write it down. And its terminal action is now what we need to solve for.
Yep.
And its terminal action, we found, was exactly the square of the terminal action of the most symmetric fitting of these boundaries.
That's pretty fantastic.
Okay, so I think this is maybe, if this is your very beginner at this and you're trying to see anything into this, like all these symbols don't mean anything to you yet, there's your 3 and your 4, I can see that would be really frustrating. At that point, though, there's still a way to try to look into these. We're trying to see the symmetry of the structure. The algebra is telling you a relationship of addition, subtraction, multiplication, and division.
Right.
The whole world's confused about what those really mean, right? Because they're assuming that there's a field that you're doing operations on exactly that way. What's the field? Nobody's answered that yet. So you should feel that that's inherently some sort of confusion. But yet these operations always hold in nature, right? So they're things that you want to investigate even though you start out confused about them. That's the point, actually. That's what we're trying to do. Okay, so here we found, well, starting back here, the perfect symmetric fitting of the boundaries, the only constant of nature that represents dimensions that match this structure, both inside and out. On one side makes a sphere, right? Under this sum or the quadrant structure, and under the product structure of the same exact constants, we get the inverse connection. Yeah. So we're getting a relationship between products and sums built into the partition structure. Follow that? Between quadrants or sums and products of our partition structure.
Well, and correct me if I'm wrong, it sounds like we're trying to figure out at this point, at least from that construction for the magnetic constant, trying to see how the product of two spheres interact with one another.
Yeah, we're fitting it together by tearing it apart, using its own parameters to twist together against themselves.
Wait. Now, two spheres coming together, isn't there something like that in math?
Yeah, the Riemann sphere.
Cool.
Square action of the minimal action, or of the most symmetric action. Okay.
That's pretty awesome. Now, and because if you're looking at that, because now if you're taking that, you're basically squaring it, taking it to a different scale, but the actual potential intensity of it, depending on these magnitudes, because we're talking about a little bit, maybe seeing the relationships of the magnitudes between the primary actions and the terminal actions. And I think that's going to be a very interesting investigation we're going to end up doing. And hey, if anyone else, basically, if this interests you, you want to come take a look, just let me earth that up. Links will be in the doobly-doo. Wouldn't that mean that gravity may be, I'm just conjecturing here, may be a very useful component to take whatever system we are constructing and allowing it to function, just based upon our knowledge of how gravity kind of works?
Yeah, this allows you to get the fitting together of these boundaries, and since you're making every other feature of reality out of constants of nature or fit together constants of nature who use the exact same boundaries, being aware that this is the weak fitting together, but it's there, you can start to take advantage of it. Right now, before looking into the world this way, we have an image that leaves us entirely blind to the inner gearwork of quantum mechanics. Once you get past a certain scale, it's all quantum mechanics, and no one has any image. It's just fuzzy. That's the view we have of the world basically right now, right? This gives you a way to look past the fuzz to see the inner gearwork, literally, how the things are breaking apart and forming the manifold shape, right? But also, the larger scales are part of that manifold. That's what it's showing. See, this exact same boundaries fitting together to make the gravitational projections. All right, let's address another recent insight of connection between the internal and external forms. The internal form is the hyperbolic figure-8 knot. The equation for that is just I times dilogarithm, two-dimensional logarithmic connection of 1 over the imaginary golden ratio minus a dilogarithm of, opposite of that, the imaginary golden ratio. Okay. this gives us the base structure of everything in our domain, right? You can change the signs of this to get all the fitted pieces that are included, but we're just looking now for a moment at the arguments. The arguments here are 1 over the imaginary golden ratio and the imaginary golden ratio, which again is equal to -1 to the 1/3. Remember, I is equal to -1 to the 1/2. That I. So these geometric numbers, so they're both on the unit circle, right? They have a radius of 1. These are both very central geometric numbers that divide the circle a different way. This divides the circle into 4 pieces. This divides the circle into 6 pieces. Okay, so it takes 6 of these to fill the circle. Okay, it takes 4 of these to fill the circle. Great. This division structure, this geometry, externally is held together just hyperbolically. Stop.
Now, real quick, Thad. When you say I divides the circle into quadrants, what do you mean by?
Here's the unit circle.
Okay.
That's 1. Okay, and 0 in the middle. Bad circle, I know, but close. And I is right
Oh, it's a 60.
I is right there. So by the time we get to I, you have to do it 4 times to get back to 1.
Oh, that's right. Okay, never mind.
Now, where is the imaginary golden ratio?
Oh, it's in between there. Or
yes,
it's another.
You can tell from what I told you, it has to be somewhere in here.
Yeah.
Right? Because it divides 6 times. You have to use that length.
Imaginary golden ratio is 60 degrees, whereas I is, okay. I think I was getting a little confused.
Yeah, that's the difference. So they have a lot in common.
Yeah.
Just different angle, the same radius, right? They're both in the unit circle. They're both dividing the circle. Great. So that was our argument. This thing that divides the circle into 6 things.
Yeah.
So our base argument here, both directions. Now externally we're saying the geometry is held together hyperbolically still, right? Not hyperbolic figure 8 naught, just hyperbolically, but it's going to end up being self-closed hyperbolic. But first let's just do hyperbolic.
Okay.
Okay, we set this, equal to y. Okay, the base equation for hyperbola. Now, at this stage, you can solve, well, actually, if you just plug it into Wolfram Alpha like this as it is, it'll automatically solve for the roots of y, which is basically doing this for you. It's saying, if you set this equal to 0, now give me which x's do solve the equation, right? So in that case, the roots of this equation, this hyperbolic connection, happen to be 1 over the imaginary golden ratio, 1 over the imaginary golden ratio squared, and the imaginary golden ratio squared.
Huh. Let's see. That's a very interesting coincidence.
Coincidence? Okay. But another thing to note here, we have how many imaginary golden ratio symbols show up in the roots of this hyperbolic construction? 1 here, 2 here, 3, 4, 5, 6. There's also 6 exact of these in play.
Oh.
And remember, what does it take to close the circle?
Oh, it takes 6 for the imaginary golden ratio.
Yeah.
Oh, groovy.
Very beautiful inversion of this. And now all we need, this assumes we're hyperbolic out to infinity. It's an explosion of structure that just continues forever. And that's not what we want. We need it to be quantized. So it has to close eventually, which means
we're going to have to do away with those pesky infinities in some way.
So we need to convert this equation, which explodes to infinity in form, and wrap it around. Say, hyperbolically, this is the balance we're interested in, but we want also our structure to, for its volume, to wrap around a circle, or to invert.
Okay.
So we're under Mobius construction. And if you're inverted, you're exactly opposite now, right?
Okay.
And that's
so you're
the
going
condition you need in order to be a closed manifold.
Okay.
So, but also we don't want to set this equal to 0. We want this to be set equal to, this closure, to be set equal to the mass gap of hyperbolic geometry. Let's draw that picture real quick again. A hyperbolic structure is this. So space-time is maintained under the balance of hyperbolic structure, like this. Then there's a sheet comes at the top, and in the bottom, and these are the double-sheeted hyperboloid. They come together, it's a double sheet, okay? And then there's another sheet that goes all the way around, a single sheet of hyperboloid.
Okay.
And, of course, the lines in the middle give us the intersection of the cone-on-cone structure that's dividing these sheets, right?
Okay.
So that's what's making the balance between these two sheets. So both of these hyperboloid sheets are now being maintained, but between them, let's get a different color, there's a gap that's left between the double-sheeted hyperboloids. There's just an exact spacing set. Now, what happens if you change that spacing?
It's not gonna work.
Well, you would still be under a hyperbolic construction, but one of different scales. So that's the scale parameter fixed into hyperbolic structure.
Okay.
And so we're going to call that the mass gap. Okay, this is the mass gap.
So we're trying to set that equal to something that would be the gap that we're looking for here.
Yeah, see this twisting just being, it's creating this entire structure. We want that twisting, two rotations that are orthogonal to each other, to be within inside some scale of mass gap of the hyperbolic structure.
Okay.
Okay, that's it. We're just stipulating that this is the structure. We're sticking to, you're allowed to get a mass gap. We want to close. We're not going to infinity. Okay, but we want that mass gap to be the one that specifies just the simplest possible closure.
Now, can you explain the I raised to the I, all parentheses, to the negative pi divided by 2?
Yeah, remember this is going to be a rotation of 90 degrees.
Right, okay.
Pi over 2 rotations. Right?
Okay, 2 rotations.
Okay, but if you put it to the I, then you're going to have another pi over 2 rotation in the system, but it's going to be orthogonal to the first one.
Okay, so you're going like half a circle, and then you're bringing it back a full circle.
There's two things twisting, and both of the twists are also orthogonal. So a twist gives you orthogonality, right? And a plane. Another twist gives you a plane, but those two planes didn't need to be 90 degrees.
Oh.
This is saying both planes are 90 degrees.
Okay.
And that we're just forming the mass gap of some size. You can put any size you want in here so far. We're going to pick a specific size. The one that matches the mass gap of reality, called the Planck mass. Okay, so we're going to swap this out with the Planck mass to have a specific scaled hyperbolic structure to the outside four-dimensional space, what we call space-time, right? So now we've got it. We've got a whole internal structure coming just from the hyperbolic figure-8 knot. We have the outside going just hyperbolically extending, right? Because here it was wrapped on itself two-dimensionally. Here it's extending out. But then we want it to also close. It has to invert on itself under extension. So that's it. Here's our equation. But now these numbers, instead of being what they were here, these roots change. They convert. Why did they convert? Well, we changed the equation. This changed, and we set it, instead of equal 0, we're looking for the place where this condition is met. Right? They changed to all of our jeux. This is what our jeux represent. It's the asymmetric hyperbolic balanced roots of our hyperbolic geometry. Much easier to see before it became asymmetric right here, right? These were pretty simple to see, and then we just extend to that. Okay, and you might remember this is a one-dimensional number. It's a one-dimensional number, two-dimensional number, and a two-dimensional number.
This is making a lot more sense. Now we're starting to develop a story about why may this be the case. And anytime you see something like the golden ratio, or I didn't know the imaginary golden ratio existed until about 6 months ago. At this thing, that you Google it, at least I Google it, the first thing you find is a mass stack exchange. And they're going through the decomposition, and then he links back to an earlier reference. That's why, number one, I totally love the internet, because I think this is the internet working as intended. We're actually utilizing it like a library of what we're looking for. What are we looking for? I don't know, but we're on an investigation here.
I know what we're looking for. We're looking for clarity. We're looking for a story that makes sense of the measurements we've made about reality, because we believe the measurements more than everything else, right? We believe they're reporting to us something real about reality. The gravitational constant is telling us something about the feature of reality that's built in. Something was there before you were born. Something is just intrinsically there. So it needs a story if you want to understand what the stuff that's intrinsically there is. Reality.
So we're trying to figure out what's going on.
We're trying to figure out what's going on. And we want to have a level of confidence. We want to have a way of measuring how confident we are. We have a way of measuring our confidence with the numbers. Right?
Okay, yeah.
We want to be able to use them as our story generators. Great. And here, another simple way to may say this is you have a projective universe. If you have any projective universe, like let's say a sphere, somehow a sphere is being projected.
Yeah.
Okay. Well, of course, that sphere needs to be inverted also in order to be continuously projected. So it's a sphere that inverts into a sphere and inverts into a sphere over and over and over. This partition construction is already talking about that on the outside. It's saying that the outside of the hyperbolic figure-eight knot is a giant sphere that's inverting on itself under constructed balance the entire time, right? So we have the smallest possible closed volume complement you can have in geometry, and we have the largest possible closed volume you can have in geometry on the outside. But that sphere, that external outside, is dividing under these partition parameters. These are the things that determine how we break up the outside. There's always four things that are breaking it up.
But that under that construction, that would mean there would be a boundary per se, or
Yes.
there would be up to a point.
Yeah, there's invented boundaries by this partitioning, right? Where if things are breaking up, then the action of breaking up makes the boundary.
That's really cool.
Yeah. All right, so we've done this several times, so I'll just throw them up on the screen again. But these numbers have products and sums that are extremely interesting. They tell us about the geometry and the connection in the geometry of our outside fitting together of this hyperbolic structure. And it's being applied to the boundaries that are being created by the breaking up of the geometry. And one of them is the point mass boundary. Guess what the other ones are?
Oh.
The other Planck boundaries. The boundaries that define the limits of measure in reality, meaning of the features that manifest in reality. Everything we've been able to measure at the very, very base are composed of just 5 dimensions. And surprisingly, from all of our measurements, we've discovered that those 5 dimensions have cutoffs, limits that you can't go past, even conceptually. They're not coherent past that. Okay? Each of them, we now call a Planck limit of some sort, Planck time, Planck length, so on, are the boundaries that we're fitting together in this story. That's what this story is about, how we're putting those boundaries together, or how we're rotating the domain hyperbolically, but inverting it externally under that hyperbolic action.
That's pretty cool. So we got 5 ingredients, 5 different things, and they're basically undergoing different geometric actions, doing a bunch of geometric stuff, and that seems to be what makes up what's going on around. Well, at this point, we're actually putting some bounds of the conversation. The boundaries are absolutely enormous and everything. They're ginormous, if you would, but there is a limit to them. And if we have the ability to construct in very elegant and beautiful ways, again, it's up to interpretation. But one of the things I noticed going through and calculating some of these constants, and thank you for taking me the full process. It's like I've literally, I don't know, I've taken more notes this week than I probably have over the past decade. And it was an absolute blast doing it, just because as we're going through, we're looking at the different geometric structures listed on Wolfram Alpha. And please just check us. If you find something awesome, let us know. But now it seems like you developed a particular method and ways to actually account for different error as we're going through to try to help go through the process.
All right, so what's the goat problem?
The goat problem. The goat problem is basically, this is something that apparently they just recently found a solution for. Okay, so for the goat problem, you've got a circle of area, and you want the goat to graze exactly half that circle. How long does the point where you tether the goat to need to be. So
Good.
that particular problem, because the goat, if you're going to be following these different geometric actions, it can do this much. So how long does this tethered position need to be for our goat friend to eat exactly half the grass? And it seems like just, oh, it's an easy problem, but when you actually get into it, geometrically, it's pretty dang complex. They didn't solve it until I think the past decade or so. And that's with modern computers and everything. They kept doing basically more of a recursion effort method. So it actually comes out to be a very specific ratio here depending on the size of the sphere. And apparently that seems to be there within some of these beautiful equations where it's like, oh, you take the square root. It's the square root of literally g sub g times I.
We've got an extra syntax symmetry that's not part of the actual symmetry, but it's fun to note. One of our favorite constants, because eventually they all become our favorite.
Yep.
The Planck length over the Planck time, and for the terminal action, is the square root of the Giesking
manifold.
Constant. Yeah.
Yep.
The square root of the Giesking constant. That's J1 minus J2. I should have erased all of that.
It was only hindered by extra geekiness. So what the claim is the speed of light has a terminal action. I thought it was just Planck length divided by the Planck time. It's like length divided by time equals the speed of light.
They all have terminal actions, and the way we break up the terminal actions are going to be either products of one-dimensional jizz or products of two-dimensional jizz, or sums of one-dimensional jizz or sums of two-dimensional jizz. And when I say sums, I also mean negative sums. So
okay, yeah.
Plus or minus signs there.
The different permutations.
Yeah. Okay, go on.
See, I mean, that's totally worth an entire video on itself, but I'm looking at that looks very simple. I was like, well, Thad, you list off all 10 digits of the speed of light, and you immediately correct me, like, there's only 9 digits that we've measured. Again, we were talking about before, the meme was, shut up and calculate. It's like, no, calculating, conversate, discuss this, try to figure out what's going on, because it's pretty fantastic.
This is the geeky index rotation here. This is the goat constant, the GG, right?
Yeah.
But here, with the I, you put a negative sign aside instead of that.
Yeah.
And square root, we're going to call it the imaginary goat ratio.
Right.
Right? So
we're just subtracting the imaginary goat ratio.
Yeah, but it's specifically also negative. That's the one we're calling the imaginary goat ratio. But we can pull the negative one out and put the I out here too.
Okay.
But when we do, look, we've swapped.
Wait. So what you're saying is the radius of the electron seems to have some connection here.
Yes, of course.
Oh.
In fact, we're dividing the whole domain and defining the radius of the proton, right? The radius of the neutron, the radius of the electron. They're all being defined as part of these constants. So the domain itself is partitioning into these exact scales.
Well, that's a beautiful thing too, because what the subject of an entire other video should do at one point is the radius of the neutron larger or smaller than that of the proton? Because we have 0 significant digits. We have approximate order of magnitude. Mm-hmm. That seems to be very interesting.
Good video, yeah.
It's a good time to be a nerd.
All right, and the terminal action on this is negative 2I times the square root of the goat constant. And the same exact J combination, the two-dimensional Thomas cross-section. The goat comes in.
That's
and
right.
The radius electron, the goat comes in.
Yeah.
But what's the difference between these two?
It's doubled.
It's just times by 2.
Yeah.
And do you remember Knuth talking about how you can use 2I as a base to get to almost all numbers? Yeah. Huh. Anyway, this one was a bit of a joke, just to be clear, right? The GGI here, I know it's small g and big G, but other than that, the notation had an extra cool symmetry.
We break the I out into the subscript.
Yeah.
Yeah, I mean, mathematically that's not correct, but at least notation-wise, I mean, yeah.
Anyway,
that's fun.
Beautiful. So, and whenever you have a constant that you know, that you can tell stories about, you can try to now apply the action of that story, right? You can try to figure out what's happening. Why is the speed of light the fastest possible speed? Well, the first answer is the intersection of the smallest possible boundaries.
Yeah.
Second answer is that intersection happens to be exactly the one that inverts as the square root of the Giesecke manifold.
Yeah, the minimal manifold. Yeah.
The minimal manifold, yeah. So
that's pretty neat.
Beautiful. All right, we'll throw up some new equations just on the screen. And just wanted to give a quick review of the progress after this entire week of crunching numbers and discussing the physical characteristics of reality. So we're getting a pattern that makes a lot more cohesive sense, right? It's just splitting into combinations of the partition parameters of a hyperbolic construction, but those combinations are always just in the ones that match our base symmetries. So J1 plus J2 plus J3 plus J4 equals
zero.
Zero.
Okay, that's the base. And then when we subtract, it's also zero.
Yep.
You're going to need more details in the back of the next edition. Because you only have the 4 right now. I usually bring it up. It's over there on the desk there. I usually cheat.
But just add those. 2 pi. But we also need to put another one. J1 squared plus J2 squared plus J3 squared.
And just for anybody's reference, you spell it Z-H-E. Because it took me a while. I had to reverse Google search that.
It's acrylic letters. So
Right.
Officially,
it technically is. Okay, fair. In a Western English or American tongue, we say je.
So why don't I go through all the trouble to write them out again? Because I really wanted to point out, remember, these are one-dimensional and these are two-dimensional. Just to make that distinction, let's put brackets around them. Doesn't change the equation, just helps for us to focus on them differently. We're going to group those two together because they're the same sort of thing. They're both one-dimensional. We're going to group these together because they're both two-dimensional. It's a partition structure that we're talking about the whole thing anyway. So we want to, how do these things break up? Well, they break up in two-dimensional pieces and they break up in one-dimensional pieces. So we're going to just pair them together in our minds. Okay? And when we're searching for the answer for the primary action and terminal action and so on, we're going to remember that these things, especially always in the terminal action, it's an intersection like this is being balanced under inversion. So it has to be part of this exact balance because this is the balance that's inverting the sphere on itself. This is literally the minimal balance that an external sphere could have if it's inverting on itself. So this partition structure is the one we're trying to stick to specifically when we're asking questions about this balance, right? So this is it. It can be this one, this one, this one, and this one. Or you could take this one and that one, meaning you could swap, you could put a minus sign there, right? You could take the sums or the differences of the one-dimensional or two-dimensionals as your search space. There, that's it. So try it on your own, right? Take the constants of nature, the whole list, we'll put it up on the screen. Here's the measured values, the codata values of all the constants of nature. Now here's the values that we're saying that the Planck constants have. And why? Because we put those values, we took the measurements, and I should take them a step back. We take all the constants of nature, and we find out each constant of nature has certain dimensions in it. This one has dimensions of length over time, right? They all have different dimensions in them. Some have the same, but they have an assortment of dimensions. That means you can take different constants of nature and combine them to cancel out dimensions, right? Pretty easy game to play, just dimensional analysis. But when you do, you end up landing, say if you intended to cancel out everything but one dimension at a time. So you find the constants of nature to combine that allow you to cancel everything except one dimension at a time. What do you have left over? Well, you have a time increment, a time number, a value. What is it? Well, it turns out it always is the Planck time, right? You can get to it several different ways from several different arrangements of constants, but every time you do from a different arrangement, the Planck time is only right out of so many. The number you get when you do it one time will give you all 14 significant digits. But we do it with a different set of constants. You get a different string of digits, but they'll be the same for the first 5.
Right. Code data has that's one of the things you notice. It's like these seem to be fundamental dimensional constants in nature, but a lot of them they're only out to like 5 significant digits or so, and that's interesting.
Yeah, so you can combine the constants in nature to get the Planck constants, but just out to the error bars that code out lists for the Planck constants. The question is, since we know we can use a Planck constants to get the constants in nature, what's the second piece? Obviously, they're all differing. They all have a different answer after a certain digit, right? Mm-hmm. So if you put together the second piece of the story, then you need, in order to do that, you have to have numbers for the Planck time. You have to have an actual string of digits. So how did we get the string of digits we have? Well, we believe this whole thing's under hyperbolic division. So we just plugged in the actual number you get from searching with this way, right, for the Planck time. We plug that number in and search for a hyperbolic way of getting there, right? And you get an equation that's hyperbolic. Say, well, that might be true. You get ones that don't look like anything, you just throw them out. But you look for anything beautiful, but specifically hyperbolic. And there aren't lots of options there. So you get the hyperbolic balance. And you do that all for every Planck constant, actually. Look for a hyperbolic balance that defines or that can get you to that place. And then you say, these are going to be the 5 different hyperbolic balances that we fit together to make hyperbolic geometry.
Oh, that's making more sense. Well, within context of the past week, that explains a lot. Okay.
Yeah, so are those numbers right? We're never going to claim something like that. What we're doing is we picked a hyperbolic structure that defines those numbers out to the digits we have and gives us the rest. Then to check to see if that's right, because those define the Planck constants all the way out, right? We take those Planck constants in every constant in nature, plug them in, and see what happens geometrically. The story that pops out is telling us more information. Does that make it correct? No, but what we're doing is we're getting to coherent, right? So we have data points that all are telling us bits and pieces of the story now, clues that we get to reveal for the first time. We get to use the skill of reading algebra, like learning how to read, right? This kind of reading is allowing us to now see into nature in a new way. See into a geometric structure. There's something going on that has something to do with, what's the Giesecke constant? Oh, the minimum possible manifold?
Some may say this is almost a new kind of science, if you would.
Yeah, we're using the new kind of science from Wolfram Alpha, right?
Basically,
That's our tool is using Wolfram Alpha. So if you haven't been introduced to Wolfram Alpha, it's a free website that you can go to. It's basically like the it's like a calculator.
It's a calculator almost combined with Wikipedia in a way, and that has the largest
wiki calculator and graphing thing.
Well, it has the largest number of basically coherent units listed more or less in the world.
It's a domain you should go to try to wander in. It's the fantastic domain to wander in, because if you're searching for things, if you're asking questions, and you come up and practice your skill of framing a question mathematically, right? If you can ask a math question, whether or not you have any idea what the answer is supposed to be, if you come up with a real good question to ask, you can put it in there and it'll always put together possible answers for you, okay? And that's a huge step. Every time you're completely ignorant what the next step is.
I never even knew until after a while. It's like, wait, just click on a number. Here are potential closed forms. What does that even mean? Oh, it's fantastic.
And it makes it really easy to follow the breadcrumb trail. Like, I don't know what that constant is. Okay, click, and then you have a whole page explaining it. And you go to the Wikipedia page and get even more information. Yeah, it's a beautiful path to follow. So I really recommend, I think we both really recommend, taking the constants of nature, the measurements we've made, and that our most serious minds trying to look into reality have come to a coherent agreement that these are the measurements of the features of reality that everything's composed of, right? Take those numbers yourself and just use the pattern that we're employing here,
the universal binomial factorization
equation, to separate the pieces of the actions in the balance and to look at what's going on. Okay, of course, we're going to keep updating with the clarity of the picture we're always at, but I think this is at a point where if you're in high school and wanting to participate, it's completely within your means to look into reality in a way that hasn't been looked into before, to start investigating these numbers on your own. You don't have to wait for a PhD to be able to start looking into the constants of nature and start comparing them and start making more larger and larger groups of cohesive comparisons between all of them, right?
I believe it was a wife's captain that once said, "The power is yours." Cool, good place to end. So this was a nice week. Thanks for joining. That's been fantastic.
In the physics monastery here, we focused on reverse engineering reality, and we made a lot of progress. Of course, the most progress you can ever make is have better measurements. So becoming aware of better measurements, thank you again, is delightful. But that was exciting all week.
All this is all built on the sum total of human knowledge right here. And we have good old Professor Wolfram, then Team Wolfram, everyone that's participated over the past 30 some odd years, just building these databases, these resources, Wikipedia, just the different videos coming out on YouTube and everything. Fantastic.
Before we wrap up, let me just frame again why this is all important. Besides being excited about being able to look into reality and get new clues, new hints to try to understand its parts, this is all important because as we get this story correct, it enables us to do more things, right? Calculus enables us to do a lot more things, right? Every connection in nature we're aware of allows us to manipulate and control things better. But what we really are after is the level of understanding that allows us to use or to create universal replication. We're talking about the story of the intersection of the boundaries in reality. So we want to eventually understand how to interface with these boundaries exactly with a machine with specific knowledge of what these boundaries are doing, and to convert the way nature would from one arrangement to another, right? So this would be universal conversion, not just to grow a plant. You could convert from any natural state, meaning you could take anything with mass that exists and put it as an input, and it could take that state, since it has mass, it has all these boundaries already wound up in it. So it takes the boundaries in it and rearranges them into the form that you wanted instead, which is what's happening the whole time in nature anyway. We're just blind to how. We know that's what's going on, we just don't know how. This is the story that puts together how. And as we get clearer and clearer on this story, we get closer and closer to having a universal replicator. And what happens then? Humanity gets the choice to escape the yoke of money, where everyone gets food for the rest of existence simply because you're a human. The same way you get air just because you're alive, the way it should be. There should never be threat or resource control over things like that. Our understanding of reality can take us past the point where anyone could ever threaten us resource-wise.
Well, that's the thing. And now we open up new opportunities where we're going to need a lot of help to do this, because recently we've hit ignition with the National Ignition Laboratory. It's like, okay, we've finally shown that we can do what we said we were going to do. That's great. Now, that actual scale, and to actually get that up to actual point where we could actually have fusion technology, that's going to be something that we're going to need to try to power something like this. We're going to need to have room temperature or better superconductors to be able to transfer that energy. It's going to be a lot of work. It's going to take so much human concentration. But it's a beautiful thing that we live in this particular time, in this particular moment, that we can actually have people participating, actually exploring the computational universe to try to help work on this, because totally it's going to be a transition period. And you have the part to be about one of the greatest stories, if not the greatest story, in the history of humanity. And we all have the ability to contribute to this right now. And one of the things that I actually I notice here is you just kind of look at what's going on with everything here. I see the mass gap, and again, maybe it's just an ontological thing, is a lot of the conflict we have is just a lack of knowledge. Lack of knowledge because of whatever situation an individual may have been placed in, whatever they may have been born into, those particular circumstances, we have the ability to at least work towards transcending that. Now, National Ignition, that's great. Less than 1% actual turnover when you could incorporate all the other numbers, whatever it might be. But, okay, I see that as nav point alpha. We're looking to get into nav point zeta, where it's literally Mr. Fusion from back to the future. You just, as long as something has mass, and it has the property of mass, you put it in. And we're going to need to fill in those gaps of that engineering, all that different computational work needed to get to building the superconductors. I've seen things from Brown University, twisted multi-layer. It's fantastic. So if we have the ability, like Thad was saying, to actually figure out to higher levels of precision what's going on, that's going to feed into engineering. And as the engineering gets better, we're going to get better data mesh from this. We're going to get the ability to tighten up. It's like I think Professor Wolfram says, in order to build a tall tower, you need a strong foundation. But as you build up that tower, that allows you to do more and more cool things. Like, that's pretty awesome.
Yep. So if you want to join the investigation and help get this story tighter and tighter, and get the understanding we have of reality to become more geometric and exact, or if we could reword it to see the inner gears of quantum mechanics, then
Cool.
please do. Please do.
Yeah, just let us know.